picking up good vibrations.
So the next example is to compute the Fourier transform of a Dirac. It turns out to be very, very easy if we recall the following property. When we have a Dirac inside an integral, we have an integral of a given function gt delta of t minus s dt. This is simply evaluating, the Dirac is centered at s, is simply evaluating this function g when t equals s. Now, if we use this property and if we replace simply x of t here by delta of t, we get the Fourier transform is equal to this integral of the Dirac e to the power of minus j omega t dt. So basically we have to evaluate this function here when t equals 0. And if we replace this function when t equals 0, we get simply exponential of 0, which is 1. So we simply get 1. And this basically means that if we were to plot the Fourier transform of Dirac, is simply a constant function equal to 1 for every frequency. Now, it's also convenient for the next example to compute the Fourier transform of a Dirac, but centered at, let's say, t0, minus t0. So now we have a Dirac centered here at t0. If we do that, we have to evaluate this function here. So we have here, instead of t, we have here delta of t minus t0. That basically means that we have to evaluate this function here when t equals t0, and we would get instead e to the power of minus j omega t0. We could have also obtained this with the properties of the Fourier transform that we'll talk about later, but for now it's important to understand that a complex exponential as a function of omega, this is a complex exponential, will lead e to the power of minus j omega t0 will lead to a Dirac in time. So a complex exponential in frequency will lead to a Dirac in time.